welcome to tonight's Space Sleep Story. If you appreciate what we do here, please like or subscribe for future relaxing nighttime space journeys. Tonight we embark on a journey to understand one of the universe's most fascinating phenomena: black holes. Regions where gravity becomes so extreme that not even light can escape. So, settle into your most comfortable position, close your eyes, and prepare to explore these cosmic enigmas from a safe distance, learning how humans discovered and photographed the invisible. Before we begin, let us prepare your body and mind with gentle breathing. Take a slow, deep breath with me now. Inhale gently for 4 counts. Hold the peace. Exhale for 6. Feel your body releasing into stillness. With each breath, you become more relaxed, more ready to contemplate the universe's most extreme objects. Let the stress of the day drift away like matter falling into a gravitational field, slowly, inevitably, peacefully. Another gentle breath as we continue our preparation. This time, notice how your chest rises and falls, a rhythm as natural as planets orbiting stars. Let my voice be your guide through tonight's cosmic journey. Hold this peaceful moment. Feel the tension leaving your shoulders, your neck, your face. With each breath, you release a little more into relaxation, preparing to float through space and time, learning about gravity's ultimate expression. Imagine yourself floating in an observation station, billions of kilometers from any galaxy's center. Safe, peaceful, with a perfect view of the cosmos. Tonight we will not fall into a black hole. That would be brief and one way. Instead, we observe from this comfortable distance, as astronomers do, learning about these remarkable objects through their effects on surrounding space, matter, and light. Black holes are not holes at all, despite their name. They are the opposite, concentrations of mass so dense that space-time curves back on itself. What is a black hole? Begin with the simplest definition: a region where escape velocity exceeds the speed of light. On Earth, escape velocity is 11.2 kilometers per second. Launch a rocket faster than that, it leaves Earth forever. But imagine compressing Earth's entire mass into a sphere just 9 millimeters across. The escape velocity at that surface would equal light speed. Nothing can travel faster than light. Therefore, nothing can escape. That boundary is called the event horizon. The event horizon is not a physical surface you could touch. It is a mathematical boundary, a point of no return. Once anything crosses it, matter, light, or information, it can never communicate with the outside universe again. The radius of this boundary is called the Schwarzschild radius, named for Carl Schwarzschild, who calculated it in 1915. The formula, R equals 2gm divided by c squared. Mass determines the size. More mass means larger horizon, but the relationship is elegant and exact. Black holes come in different sizes. Stellar mass black holes form when massive stars die. They typically contain 5 to 20 solar masses, compressed into a sphere 15 to 60 kilometers across, the size of a small city, yet containing more mass than our entire sun. Supermassive black holes live at galaxy centers. They contain millions to billions of solar masses, yet remarkably, their average density is less than water, A billion solar mass black hole has a horizon 3 billion kilometers across, 20 times Uranus's orbital distance. At the center of every black hole, mathematics predicts a singularity, a point where all the mass concentrates, where density becomes infinite, where space-time curvature becomes infinite. But this is where our physics breaks down. General relativity, Einstein's theory of gravity, cannot describe what happens at infinite density. We need a theory of quantum gravity that physicists are still developing. The singularity may not be truly infinite, but rather a placeholder for physics we don't yet understand. And that's perfectly acceptable. The story of black holes begins with theory, not observation. In 1783, British natural philosopher John Michell imagined what he called dark stars. He calculated that a body with the sun's density, but 500 times its radius, would trap light by sheer gravitational pull. Remarkably prescient, considering he had no framework of relativity, working only with Newtonian gravity. He even proposed detecting these invisible objects by watching their gravitational effects on visible companion stars. That method is still used today. Carl Schwarzschild found the mathematical answer in 1915. Einstein had just published General Relativity, his revolutionary theory describing gravity as space-time curvature. Schwarzschild was serving on the Russian front during World War I when he solved Einstein's field equations. He identified the critical radius where unusual properties emerge. Time slows, space curves dramatically, escape becomes impossible. He mailed his solution to Einstein, who presented it to the Prussian Academy. Months later, Schwarzschild died of illness at age 42, but his solution remains foundational. Not everyone accepted the implications. Arthur Eddington, the British astronomer who confirmed Einstein's relativity during the 1919 solar eclipse, rejected the idea of complete gravitational collapse. He insisted there should be a law of nature to prevent a star from behaving in this absurd way. For decades, many physicists dismissed black holes as mathematical curiosities, not physical reality. The equations predicted them, but surely nature would find a way to avoid such extremes. Sometimes our intuition resists what mathematics clearly shows. Robert Oppenheimer and Hartland Snyder proved the mathematics in 1939. They calculated what happens when a massive stellar core exhausts its nuclear fuel and collapses. If the core exceeds about 3 solar masses, nothing can stop the collapse. Not electron degeneracy pressure, which supports white dwarfs. Not neutron degeneracy pressure, which supports neutron stars. Beyond those limits, gravity wins absolutely. The core collapses beyond all known stopping points, forming what they called a frozen star, because from outside it appears frozen at the horizon eternally. The term black hole came much later. John Wheeler, the American physicist, popularized it during a lecture in 1967. Before that, physicists awkwardly referred to gravitationally completely collapsed objects or frozen stars. Someone in Wheeler's audience suggested black hole, and the name captured the essential property perfectly. Dark because no light escapes. Mysterious because we cannot see inside. One way because nothing returns. Sometimes the right word makes an abstract concept tangible. Wheeler later said, "Science needs poetry too." How do black holes form? There are three main pathways. The most common is stellar collapse, when a star exceeding 20 to 25 solar masses exhausts its nuclear fuel. The core collapses catastrophically in less than 1 second. The outer layers rebound in a spectacular supernova explosion, visible across millions of light years. But the core continues falling inward, compressing beyond the neutron degeneracy limit. What emerges is a stellar mass black hole, typically 5 to 20 solar masses, with a radius of 15 to 60 kilometers. A city-sized object born from a star. Supermassive black holes present a greater mystery. Virtually every large galaxy has one at its center, containing millions to billions of solar masses. Our Milky Way hosts Sagittarius A star, 4.15 million solar masses, sitting 26,000 light-years away at the galactic heart. But how do such monsters form? Likely several processes contributed. Direct collapse of massive gas clouds in the early universe. Runaway mergers of stellar mass black holes over cosmic time. Collapse of extremely dense star clusters. Probably all three mechanisms operated, building the supermassive population we observe today. The third type remains largely hypothetical. Primordial black holes could have formed in the first second after the Big Bang, from density fluctuations in the infant universe. They might range from microscopic, just 10 to the -8 kilograms, to thousands of solar masses. Some physicists suggest primordial black holes could explain dark matter, the invisible mass that outweighs visible matter 5 to 1. But most mass ranges have been ruled out by observations. If they exist, they must be rare or confined to narrow mass windows. The search continues, using gravitational lensing surveys that watch for telltale magnification of background stars. Understanding black hole formation required understanding stellar evolution. Subrahmanyan Chandrasekhar calculated in 1930 that white dwarfs, the remnants of stars like our Sun, cannot exceed 1.44 solar masses. Beyond that limit, electron degeneracy pressure is insufficient to resist gravity. Arthur Eddington famously dismissed Chandrasekhar's result, publicly humiliating the young physicist. But Chandrasekhar was right. The limit is real, confirmed by countless observations. He received the Nobel Prize in 1983, decades after the discovery. Mathematical certainty eventually overcomes authoritative dismissal. The Tolman-Oppenheimer-Volkoff limit extends the concept to neutron stars. Neutron stars can exist between about 1.4 and 3 solar masses, supported by neutron degeneracy pressure. Beyond 3 solar masses, even neutrons cannot resist. This establishes the boundary. Below 1.4 solar masses, white dwarf. Between 1.4 and 3 solar masses, neutron star. above 3 solar masses, black hole. Nature provides these endpoints for stellar evolution, and massive stars are destined for the black hole fate. Our sun is safe, too small to undergo this transformation. Rotating black holes are more complex than stationary ones. Most real black holes possess angular momentum inherited from their parent star's rotation. Roy Kerr solved Einstein's equations for rotating black holes in 1963, revealing extraordinary features. A rotating black hole has 2 boundaries: the event horizon, the true point of no return, and an outer region called the ergosphere, where space-time itself is dragged around the black hole. Inside the ergosphere, nothing can remain stationary. Space itself flows like a river around the rotating mass. This is frame dragging, one of relativity's strangest predictions. Black holes can spin at tremendous rates. The maximum rotation occurs when the surface of the event horizon moves at the speed of light. At this limit, the black hole is called extremal. Spinning black holes possess angular momentum and mass, but remarkably, nothing else. They have no chemical composition, no temperature, no magnetic field of their own, only mass, spin, and possibly electric charge. John Wheeler summarized this as, "Black holes have no hair," meaning no additional distinguishing features. All information about the matter that formed them is lost, except these 3 numbers. This simplicity is both elegant and mysterious. X-ray binary systems reveal stellar mass black holes. The black hole strips material from a companion star. Gas spirals inward, forming an accretion disk. Friction heats the material to 10 million degrees Kelvin, emitting intense X-rays with millisecond variability. Cygnus X-1 was discovered in 1971 by the Uhuru X-ray satellite, a compact object orbiting the blue supergiant star HDE 226868. Orbital analysis yields a mass of 14.8 solar masses, located 6,070 light-years away, the first strong black hole candidate. Stephen Hawking initially bet against Cygnus X-1 being a black hole. "A hedge bet," he explained. If wrong about black holes existing, at least he'd win a subscription. He conceded the bet in 1990 as evidence accumulated. The most convincing evidence comes from stars orbiting Sagittarius A. Andrea Ghez and Reinhard Genzel led independent teams, tracking infrared observations through the dust for decades, measuring precise stellar orbits with remarkable patience. The S2 star completes a 16-year elliptical orbit around Sagittarius A star. Closest approach, 17 light-hours from the center. That's 120 astronomical units. Velocity peaks at 7,650 kilometers per second. That's 2.55% light speed. Kepler's laws yield the central mass. 4.15 million solar masses contained in a region smaller than our solar system. It can only be a black hole. Both teams shared the 2020 Nobel Prize in Physics. Andrea Ghez reflected on the decades of work. "You need patience for this science," she said. "Each observing run adds 1 point to a multi-decade campaign. But the result is undeniable. 4 million solar masses in a tiny region." Reinhard Genzel spoke of healthy scientific competition. Andrea's group and mine independently reached the same conclusion. Different telescopes, different techniques, different analysis methods. Both found identical results. That's how you know it's real. Gravitational lensing reveals black holes through bent light. According to general relativity, black holes bend passing light. They can magnify background objects, distort them, create multiple images. If perfectly aligned, they produce an Einstein ring. This technique detects black holes even without accretion disks. Microlensing surveys search for primordial black holes. Using the warping of spacetime as a cosmic magnifying glass, revealing invisible mass through its gravitational signature. Quasars are the most luminous, persistent objects in the universe. Supermassive black holes actively accreting matter in distant galaxies. A single quasar outshines an entire galaxy, powered by billion solar mass black holes, converting infalling matter to energy. Martin Schmidt identified quasar 3C273 in 1963. Extreme redshift implied enormous distance, 2.4 billion light-years away, with astonishing luminosity. This launched the search for the power source. Supermassive black holes confirmed later. The peak quasar era occurred when the universe was 2 to 3 billion years old. Virtually every large galaxy has a supermassive black hole at its center, though most are currently quiet, including our own Sagittarius A star. Some black holes launch relativistic jets, collimated plasma streams traveling at near light speed. Magnetic fields thread through the accretion disk, extracting rotational energy, accelerating particles to 99.99% the speed of light. The M87 jet extends 5,000 light-years from the galactic core. Powered by a black hole of 6.5 billion solar masses, a cosmic lighthouse visible across intergalactic space. Energy transported across millions of light-years. X-ray astronomy has revealed the black hole population. Successive space observatories have mapped the invisible. Uhuru in 1970, Einstein Observatory in 1978, ROSAT in 1990. Chandra and XMM Newton have operated since 1999. Collectively, they detected thousands of black hole candidates. In X-ray binaries across our galaxy, in active galactic nuclei across cosmic distances, revealing a universe populated with these extreme objects. Now we turn to listening to space-time itself. On September 14, 2015, gravitational waves were directly detected for the first time. Two black holes merged 1.3 billion light-years away. The merging black holes had masses of 36 and 29 solar masses. The final 0.2 seconds before merger produced detectable space-time ripples reaching Earth. 3 solar masses converted entirely to gravitational wave energy, pure energy radiating through the cosmos. The peak power output was extraordinary, 50 times all the stars in the observable universe combined. For a fraction of a second, this merger outshone everything. The signal appeared simultaneously at Louisiana and Washington detectors. Relativistic jets emerge from some black holes, launching collimated plasma streams at near light speed. Magnetic fields thread through accretion disks, extracting rotational energy via the Blandford-Znajek process. Particles accelerate to 99.99% light speed. M87's jet extends 5,000 light-years from its core. X-ray astronomy evolved through successive space observatories, revealing black hole populations across the universe. Einstein Observatory operated from 1978 to 1981. Chandra X-ray Observatory, launched in 1999, continues observing today. These missions collectively detected thousands of black hole candidates. LIGO's development spanned decades from conception to detection. The Laser Interferometer Gravitational Wave Observatory was conceived in the 1980s. Initial LIGO operated from 2002 to 2010 without detection. Advanced LIGO came online in 2015 with 10 times greater sensitivity. Within days of reaching operational sensitivity, LIGO achieved its first detection. The breakthrough came after 35 years of development, patient engineering, and persistent belief. Rainer Weiss, Kip Thorne, and Barry Barish received the 2017 Nobel Prize in Physics. The Event Horizon Telescope collaboration connected 8 radio observatories on 4 continents. This created an Earth-sized virtual telescope using very long baseline interferometry. The array achieved resolution of 20 microarcseconds, equivalent to seeing a basketball on the moon. Observations required atomic clock precision synchronization and petabytes of data. Hard drives were physically flown to correlation centers because the data was too massive to transfer electronically. Then, 2 years of careful analysis transformed raw observations into the final image. Sagittarius A star imaging proved more challenging than M87 star. Our galaxy's black hole exhibits rapid variability, with gas orbiting in minutes rather than days. This required sophisticated imaging algorithms to reconstruct a stable picture. The image was released in May 2022. Tidal disruption events occur when stars wander too close to black holes. Tidal forces exceed the star's self-gravity, tearing it apart completely. Stellar material streams into the accretion disk, producing characteristic optical and X-ray flares. These flares last months to years. We observe dozens of tidal disruption events per year in distant galaxies. Each event provides a cosmic laboratory revealing black hole properties. The disruption pattern depends on the black hole's mass, the star's composition, and the approach geometry. Stephen Hawking revolutionized black hole physics during the 1970s. He proved black holes have entropy proportional to their horizon area. He predicted black holes emit thermal radiation through quantum effects near the horizon called Hawking radiation. Hawking radiation means black holes aren't completely black. They glow faintly. But if they evaporate over immense timescales, what happens to information that fell in? This creates the information paradox. Quantum mechanics forbids information destruction, yet black holes seem to destroy it. Black holes serve as cosmic architects, not just exotic curiosities. Every large galaxy contains a supermassive black hole at its center. The black hole's mass correlates with the galactic bulge mass. Black holes influenced galaxy formation and evolution throughout cosmic history. During the quasar era, when the universe was young, black holes regulated star formation. Their energy output shaped galactic structure. Jets transport energy across millions of light years. Black holes both destroy through tidal disruption and accretion. They also create triggering star formation via shock fronts. Time dilation near event horizons reveals relativity's profound nature. From external perspective, infalling objects appear frozen, yet from the infalling frame, crossing occurs in finite time. Both perspectives are correct. Relativity unites them. This is the universe's deepest lesson about reference frames. Observation itself shapes reality. Our sun is too small to form a black hole. It will become a white dwarf in 5 billion years. But massive stars are destined for this fate. Betelgeuse, Rigel, and Eta Carina will eventually collapse beyond neutron stars. They will become black holes, gravitational monuments to stellar death. Current stellar black holes are corpses of massive ancient stars. They exhausted their fuel billions of years ago. They persist essentially forever. Black holes prove general relativity correct under most extreme conditions. Space-time curvature, time dilation, gravitational waves, all exactly as Einstein predicted. Gravitational waves carry new revelation. September 14, 2015, LIGO detected ripples in space-time itself. Two black holes merged, 1.3 billion light-years away. So the final 0.2 of a second before merger produced detectable waves. 3 solar masses converted entirely to gravitational wave energy. Peak power, 50 times all stars in observable universe. The signal appeared simultaneously at Louisiana and Washington detectors, 7 milliseconds apart, light travel time, exact waveform predicted for merging black holes. By Kip Thorne proposed LIGO in the 1980s. Most astronomers skeptical. Initial LIGO found nothing in 9 years. Then advanced LIGO operated 4 days and detected GW 150914. "35 years from idea to discovery." Rainer Weiss measured space-time distortion smaller than a proton diameter. Over 4-kilometer distance. Triumph of precision engineering and patience. LIGO LIGO and Virgo have now detected 90 gravitational wave events, most from merging black holes, typical stellar mass binaries 5 to 50 solar masses each, peacefully. August 2017 brought neutron-star merger, gravitational waves plus electromagnetic counterparts across the spectrum. Confirming neutron-star mergers forge gold, platinum, and uranium. GW190521 detected intermediate mass black hole merger, producing 142 solar mass remnant. Component masses challenged theoretical limits, evidence for intermediate mass population. Future space-based detectors will extend our hearing. LISA planned for the 2030s, 3 spacecraft in triangular formation separated by 2.5 million kilometers. LISA will detect supermassive black hole mergers across cosmic time, revealing black hole population evolution. Binary white dwarfs and extreme mass ratio in spirals. Now consider imaging the event horizon itself. Event Horizon Telescope collaboration coordinated 8 radio observatories on 4 continents, creating Earth-sized virtual telescope. Resolution 20 microarc seconds. Like seeing a basketball on the moon. Atomic clock synchronization and petabytes of data. Hard drives physically flown to correlation centers. Target M87 star, supermassive black hole 55 million light-years distant, 6.5 billion solar masses. Event horizon diameter 38 billion kilometers. .5 times Pluto's orbital distance. Observations April 2017. Image released April 2019. Orange ring surrounding dark shadow. Photons orbiting at 1.5 Schwarzschild radii, creating bright photon ring. Central shadow, where light falls inward forever. Shep-Doeleman Coordinated Global Telescope Network. Weather had to cooperate everywhere simultaneously. Then 2 years of analysis. That image is real photon orbit. Katie Booman developed algorithms for image reconstruction. Multiple independent methods produced consistent result. Ring-like structure exactly as predicted. Sagittarius A star proved more challenging. Rapid variability as gas orbits in minutes. Image released May 2022. Ring structure consistent with predictions. However, our own galaxy's black hole finally revealed. 26,000 light-years away, 26,000 black holes continue their eternal existence, gravity pulling inward forever, event horizons marking one-way boundaries. Stellar corpses drifting through galaxies, supermassive anchors at galactic centers, cosmic monuments to gravity. Rare mergers ringing space-time like bells. gravitational waves propagating across cosmos, the universe operating. We float peacefully at safe distance, understanding them slightly better than our ancestors, comfortable. Black holes prove reality exceeds imagination. Light trapped by gravity. Time stopping at horizon. Mathematics predicted what observations confirmed. Equations describing reality, even when seeming absurd. We progressed from speculation to detection to imaging. Single human lifetime. Patient observers. The universe reveals secrets to those with good instruments. Open minds, persistent curiosity. Black holes influenced galaxy formation and evolution, not just exotic curiosities, fundamental components. Every large galaxy has supermassive black hole at center. Mass correlating with bulge. Cosmic architecture. Quasar era, when universe was young. Black holes regulated star formation through energy output. Time dilation near event horizon. Infalling objects appear frozen from outside. Relativity unites perspectives. Our sun, too small to form black hole, will become white dwarf instead. 5 billion years. Massive stars destined for this fate. Betelgeuse, Rigel, eventually collapsing beyond neutron stars. Current stellar black holes are ancient corpses, stars exhausted billions of years ago. Gravitational monuments. Black holes prove general relativity correct. Under most extreme conditions imaginable, Einstein predicted. From Mitchell's 1843 speculation to EHT's 2019 image. Human persistence. Rest peacefully. Black holes continue. Event horizons remain. Peacefully. Drifting gently, understanding deepened. Space-time curves. You rest. Sleep now, floating peacefully. Black holes continue their gravitational persistence across the universe. Event horizons mark the one-way boundary forever. Space-time curves around invisible mass eternally. accretion disks glow orange from heated, infalling matter. Gravitational waves ripple outward from distant mergers. Mathematics predicted reality before observations confirmed it. Human curiosity transformed impossibility into understanding. From Schwarzschild to LIGO to EHT imaging. "236 years of patient discovery." Tonight, manifest with increased cosmic comprehension. Black holes, natural stellar endpoints, no longer frightening. The universe operates according to relativistic laws. Information paradox and quantum gravity tomorrow. Sleep peacefully under gravity's gentler influence here. Understanding deepens. Cosmos becomes less mysterious. Rest, sleep, rest, peace.